Hi, everybody. It's Professor Mitchell. We're continuing with Chapter 6. So now we're doing Section 6.2, which is real applications of normal distributions. So if you just watched the video on 6.1, standard normal distribution, that's most of what you need to know for this next section. It's just that now we will be able to work with other normal distributions that are not the standard one. Okay. All right. And that is the key concept of this section, working with normal distributions that are not standard. Okay. And the way that we're going to do that is we're going to standardize a normal distribution by using the z-score formula, it turns out. And here is your z-score formula again. We've worked with this thing before. I think maybe when we worked with it before, it was written in terms of the sample notation. It might have said z equals x minus x bar divided by s. But it's the same thing. Okay. So just remember that your standard normal distribution is a distribution of z-scores. Okay. All right. All right, so here's the idea. You start off with some non-standard normal distribution with a mean of mu. So mu could be any number. And let's say that you're trying to find the area to the left of x. By putting that value of x into the z-score formula, it converts your non-standard normal distribution into standard. So the new normal distribution has a mean of 0 and a standard deviation of 1. And all of these things that live along the bottom are z-scores. Okay, so here are the steps to finding areas with a non-standard normal distribution. First thing I recommend is draw a picture. Drawing the picture is so helpful. It's easy to make mistakes like forgetting that you're looking for an area to the right, and so you have to do 1 minus. That is super easy to forget, especially if you don't draw a picture. Okay. So I do recommend drawing the picture, label the mean and any specific x values, and then shade the region that represents the probability that you want. Okay. Step 2. For each relevant value x that is a boundary for the shaded region, convert that to a z-score using the formula that you also see behind me. Okay. And then, to convert that area to a z-score, with some technologies, that step can be skipped, like certain graphing calculators. You can just put in the mean that you have and the standard deviation that you have, and you don't have to do that part. Okay. Okay, and then once you've got it converted over to a standard normal distribution, you can either use technology or your table A2 to find the area of that shaded region. And that area will be your answer. Okay, so our first example, heights of men are normally distributed with a mean of 68.6 inches and a standard deviation of 2.8 inches. Find the percentage of men who are taller than a shower head, which is installed at 72 inches. Story of my life. Okay. All right. So the first step is to draw the picture. So that picture kind of looks like this. All right. I had to edit some spoilers out of this picture. So here's the mean of 68.6 inches right in the middle. Here is the relevant x value, 72 inches up here. And we're looking for the proportion of men who are taller than 72 inches. Okay, so once you've drawn the picture, Now we're going to convert everything over to our standard normal distribution. So the only relevant x value is that 72 inches. So I'm going to find that z-score by putting in the mean, which is 68.6, and the standard deviation, which is 2.8. It turns out that 72 minus 68.6, and then divide by 2.8, that comes out to 1.21. So that height of 72 inches has a z-score of 1.21. Okay, so now that we have this picture, let me just direct your attention to the 0 and the 1.21. We don't really need these other values anymore. Use the table to find that the cumulative area to the left of that z-score is 0.8869. So I'm going to assume at this point that you know how to find that in the table. Okay. So that's this area over here, 0.8869. And because we're looking for an area to the right, that's why I have to do 1 minus that area that I found in the table. 1 minus 0.8869 comes out to 0.1131. You might notice that it kind of looks like I've typed this this 0.1131 over top of something else. And that's exactly what I did, right? Because the people that put this together, they used technology to find that area, and it came out a little bit different because their z-score was not rounded, all right? I'm assuming that most people who are doing this are not using technology. I don't really believe in making people buy graphing calculators if they don't already own them. So I didn't want people not using a graphing calculator to be confused about where they got this other number. So I say let's just stick with the one that's in the table. Okay. So that area, according to the table, the area to the right, is 0.1131. That's what we'll go with. All right, the proportion of men taller than 72 inches is 0.1131. So that's about the percentage of men who aren't going to like the shower head being installed at 72 inches. Okay. All right, helpful hints for cases in which the area is known and we have to find the relevant values. So this is, again, what I call the backwards problem. You're given an area and you have to find the mystery x value that goes with that area. In the last section, we talked about how to find the mystery z value. So this is going to be going just one step further. Number 1, draw a graph. Can't say that enough. It's so helpful. Whoops, I just noticed a typo. Normal provability distributions. That's not what they meant. Okay. Probability. There we go. Didn't even notice that before. Number 2. Oops. We only have one thing on there. Okay, so draw a picture. That's all you need from there. Number 2, don't confuse z-scores and areas. Said that in 6.1, right? So the z-scores are the numbers along the bottom. They indicate how many standard deviations above or below are you. And then the area is the region under the curve. The z-scores are on the left, and on top of the table, the areas are inside the table, in the body of the table. Okay, and then make sure that you understand, are you working with the right side or the left side? Okay. The table only deals with left side. So if you're doing a right side problem, your very first step should be to find the complement of that area, okay? So that you know what area to look for in the table. Okay, number 4, a z-score must be negative whenever it's located on the left side of your normal distribution. It has to be negative. Remember that areas or probabilities are always between 0 and 1. Areas are never negative. Z-scores can be negative. Areas can't be. Okay, so to find values from known areas or probabilities, number one, sketch the curve, shade the appropriate region. Number two, if you're using technology, make sure you know how to use it. If you're using the table, remember that the table only does areas to the left. And then, what's typically going to happen in this section when you're doing a known area problem is you take the known area and convert it to a z-score, but then you have to convert that z-score back into a raw score. Okay? And there are a couple of different ways to do that. Number one, you can just use your regular z-score formula and solve for x. So you'll take your known area, find the z-score that goes with that known area. You will already know the mean and the standard deviation, so then you just have to solve this thing for x. So that takes a little bit of algebra to do that. I mean, it's pretty simple algebra, but if you don't feel like doing any algebra, then you can use a different version of this formula that is already solved for x. And that version looks like this. When you solve this formula for x, you get that x is mu plus z times sigma, and you don't really need those parentheses. So maybe I'll go with that. That's a little simpler. I'm not usually a big fan of having another formula, but that's fine. All right. And then refer to the sketch of the curve to verify the solution makes sense in the context of the graph and in the context of the problem. Okay? You know, sometimes it helps at this point to put your answer in a complete sentence. I'm always pestering my algebra classes to do that, because sometimes you get answers that if you put it in a complete sentence, you would say, hey, wait a minute, that doesn't make a lot of sense. Okay. All right, so let's look at this problem. When designing equipment, one common criterion is to use a design that accommodates 95% of the population. We have seen, probably in a previous example that we didn't go over, that only 46% of women satisfy the height requirements for U.S. Air Force pilots. Pilots cannot be too tall. All right, so there is a maximum height requirement for pilots. What would be the maximum acceptable height of a woman to be an Air Force pilot if the requirements were changed to allow the shortest 95% of women to be pilots? So in other words, we want to find the 95th percentile of heights of women. So we need to have some information about the heights of women. They are normally distributed with a mean of 63.7 inches and a standard deviation of 2.9 inches. And then they have this little question at the end. In addition to the maximum allowable height, should there also be a minimum required height? I'm not as worried about that part. Okay, so we'll try to get through as much of this as we can in this video, and if it doesn't all make it, look for the rest in part 2. Okay, so the first thing we're going to do is draw a picture. So this picture represents my heights of women, normally distributed. Here is the mean of 63.7, and we want to find the mystery height that cuts off the bottom 95%. All right, the second step is to figure out what z-score cuts off the bottom 95%. So I'm going to look around in my table. I know that z-score will be positive. It has to be if it cuts off the bottom 95%. 0 cuts off the bottom 50%. So anything that cuts off more than 50% has to be positive. Well, 0.9500 is one of those z-scores that is not found in the table. However, I noticed something interesting in my table. There's a little star here right between 0.9495 and 0.9505. And if I follow this arrow, there is a note that says that the z-score that goes with area of 0.9500 is 1.645. That is a common z-score that we're going to be using all the time. In fact, I see it over here too. Okay. Now, normally, if you're looking for a specific area in the table and you don't find it, I usually just recommend go with the one that's the closest. Like if I was looking for 0.9000, I would just use this because that's the closest. Okay. So we will go with a z-score of 1.645. That's how they got this thing that you may have noticed at the bottom of the picture. Okay. All right, so area of 0.9500, look for that area. And there's a footnote saying that that z-score is 1.645. Okay. So now what I have to do is convert that z-score of 1.645 back to a woman's height. Okay. Using the fact that women's heights are normally distributed with a mean of 63.7 and a standard deviation of 2.9. Okay. So we will use, oh, they're using this formula. Okay. You might find it a little simpler to use this one. Okay. Doesn't require any algebra to use this one. Okay. But they're using this formula. So 1.645 equals x minus 63.7 over 2.9. Oh, I need to show my work here, I think. Okay. So the way that you solve this for x is just multiply both sides by 2.9. I wish they had used the other formula. I would have fixed it if I'd noticed that. Okay. So if you multiply both sides by 2.9, these things cancel. Okay. 2.9 times 1.645 is 4.7705. 4.7, I'm just going to write 4.77. And then if you add 63.7 to both sides, you get the answer that they found right here. Okay. Add 63.7 to both sides and you get that x is about 68.47. Oh, there it is. I would have just done it that way if I had remembered that that was there. Okay. So I think that thing on the bottom is easier. Okay. All right, we are just about done. Let's just state our answer here. Okay. All right, so if I'm going to allow the 95% shortest women to be Air Force pilots, then that means I'm going to allow anybody who's less than about 68.5 inches tall. And then for that little question at the end, which kind of had nothing to do with any of this, there should be a minimum height requirement so that the pilot can reach all the controls. All right. I don't know that I would have come up with that answer, but anyway, there it is.